Good day, everyone. Good day to our panel. Today, we will be presenting our thesis proposal titled Design, Fabrication, and Analysis of a Savonius-type Wind Turbine Made from Bamboo along Circumferential Road 6, presented by Mark Chan, Armand De Castro, Jean Estrella, Sean Umali, with our thesis advisor, Erickson Di Maunahan. Next slide. Wind turbines are devices that convert the wind's kinetic energy into electrical energy. Similar to the effect on airplane wings, wind flows over the blades creating lift or drag forces, which causes the blades to turn. The blades are connected to a drive shaft that turns an electric generator, which produces electricity. Wind turbines are manufactured in a wide range of sizes with either horizontal or vertical axis. They are an increasingly important source of intermittent renewable energy and are used in many countries to lower energy costs and reduce reliance on fossil fuels. Next slide. A type of wind turbine is the unconventional Savonius wind turbine, which uses drag forces to rotate the rotor with its blades in the shape of half cylinders. The Savonius rotor has proven its performance due to its simple design, low cost, and low starting torque at low wind speeds. A three-bladed design for the turbine shows optimal efficiency for the Savonius-type turbine. The Savonius-type vertical axis wind turbine can operate at any wind direction compared to the horizontal axis wind turbine, wherein it relies on wind moving at a single direction, thus requiring the use of integrate technology for facing the direction of the wind. Such characteristics of vertical axis wind turbine make it suitable for small-scale and energy-grid applications in urban settings. Next slide. Bamboo is known for its high strength at an inexpensive cost and wide availability. Bamboo can be used as a sustainable and durable blade material for wind turbines. Other parts for the wind turbine can be made from low-cost and recycled materials. Next slide. Studies and current application of wind turbines show favor for the horizontal axis wind turbine type as it is more suited for large-scale applications. However, horizontal axis wind turbines are difficult to implement large-scale nature. Vertical axis wind turbines can run at low wind speeds and virtually anywhere compared to horizontal axis wind turbines. Vertical axis wind turbine is fundamentally easier to construct, less expensive, and more aesthetically pleasing. Next slide. This study introduces the use of the vertical axis wind turbines for converting wind energy into electrical energy in the Philippines while using bamboo as a blade material. The wind turbine as a source of renewable energy is a fairly small sector, and the type of turbines used are mostly horizontal axis turbines for large-scale applications. Next slide. The general objectives of the research are to design and develop a vertical axis wind turbine made from bamboo and other low-cost materials, which would harness the abundance of wind energy present in Circumferential Road 6 along Laguna Bay to convert the harnessed wind and convert it to a electrical energy. The study also aims to identify the efficiency and power output of the turbine through computing the tip speed ratio, power coefficient, and torque coefficient. Next slide. For the specific objectives, to conduct a drive-through along Circumferential Road 6 to identify an open area that is suitable for installing vertical axis wind turbines, to determine the wind velocity in the area in designing the Savonius-type vertical axis wind turbine, to design and fabricate a Savonius-type vertical axis wind turbine, and to integrate sustainability to wind turbines through bamboo and other low-cost materials. Next slide. To measure the revolutions per minute, power output, and identify the torque, and to determine the efficiency and performance of the developed vertical axis wind turbine by calculating the tip speed ratio, coefficient of performance, and the static torque coefficient. Next slide. The study introduces a sustainable and efficient alternative source of electrical energy. Furthermore, the applied turbine's design and material are achieved through an economical solution which can save in electricity expenses for the local area. The analysis of the drag forces involved in the turbine's design can help improve the efficiency of the uncommon and neglected Savonius-type turbine. The application of Savonius-type vertical axis wind turbine design is a new premise for the wind energy sector in the Philippines that makes up only a small percentage of the total energy output of the country. Thus, gathered and analyzed data of the study can elaborate and help future researchers regarding the limited knowledge on the country's wind energy applications. Next slide. Study the application of wind turbine that converts wind energy into electricity. And also the researchers will analyze its drag forces. The researchers will be using a three-bladed Savonius-type vertical axis wind turbine, and its blades will be made in bamboo materials. The wind turbine will be placed in Circumferential Road 6. Also, the researchers will analyze the wind turbine performance and efficiency using the calculations of its tip speed ratio. Next slide.
For the optimal design of novel blade profile for Savonius wind turbines, in our related studies, it is related with our study as it also designs and analyzes a Savonius-type vertical axis wind turbine and suggests its advantages over horizontal axis wind turbines and other types of vertical axis wind turbines in applications of decentralized wind energy generation in urban areas. In vertical axis wind turbine, static rotor aerodynamic coefficients, but it is similar with our study as it also analyzes the drag forces involved in the optimal design for the improvement of self-starting capability of a Savonius-type vertical axis wind turbine. In estimation of power in low-velocity vertical axis wind turbine, it's related with our study as it designs, constructs, and analyzes a vertical axis wind turbine. And in highway power generation using low-cost vertical axis turbine, it is similar with our study as it generates power using vertical axis wind turbine. Next slide, please. In performance analysis, design, and manufacturing of vertical axis wind turbine, it is related with our study as it designs and analyzes vertical axis wind turbine. And in self-starting aerodynamics analysis of vertical axis wind turbine, it is similar as it also designs and analyzes vertical axis wind turbines. In both studies, they used a Darius type of vertical axis wind turbines, whereas our proposed research study tackles on Savonius type vertical axis wind turbines. In the analysis and implementation of a drag type vertical axis wind turbine for small distributed wind energy systems, it is related with our study as it analyzes vertical axis wind turbines in urban environments, and in the effect of drag on the performance for an efficient wind turbine blade design. It is similar with their study as it focuses on drag forces. Next slide, please. In numerical study of 2 and 3-bladed Savonius wind turbine, it is similar with their study as it studies vertical axis wind turbines, especially the Savonius type. And in analyzing and designing Savonius wind turbines, it is similar with their study as it analyzes and designs vertical axis wind turbine. However, in this study, torque analysis was used, whereas in our proposed research study, it focuses on the drag forces. In an experimental study on the performance of Savonius wind turbines related with the number of blades, it is similar with our study as it studies, designs, and the performance of the vertical axis wind turbine. And in CFD analysis of Savonius vertical axis wind turbine, it is similar with their study as it tackles the effects of drag forces on Savonius type vertical axis wind turbines. Next slide, please. In Savonius wind turbines, a review of recent advances in design and performance enhancements is related with our study as it studies the functions of vertical axis wind turbines and how to improve it. In reviewing the feasibility of wind turbine technologies for highways energy harvesting, implementation of a highway wind power generation using vertical axis wind turbine to automatically power a street lamp, and vertical axis wind turbine for highway application. These studies are all similar with their studies as it implements vertical axis wind turbines in highways. However, they are different as some studies use the power generated to power a street lamp, where our study focuses on powering a battery. Next slide, please. In CFD, study of a Savonius wind turbine on a rooftop is similar with our study as it focuses on the use of vertical axis wind turbines. However, in this study, the vertical axis wind turbine was placed on a rooftop, while our research study will be focusing on installing vertical axis wind turbines in highways. In aerodynamic drag and lift forces, approaches on a movable wind turbine, it is similar with our study as it analyzes the drag forces involved in vertical axis wind turbines. And in design and construction of vertical axis wind turbine, it is similar with our study as it designs and constructs vertical axis wind turbines. Next slide, please.
So in this chapter, it presents theories and formulas which are relevant to the study. The chapter includes the parameters in design, mechanical transmissions, and voltage output. The chapter also consists of the mechanical properties of bamboo and the design of three-bladed Savonius-type wind turbine. In the input, we have the wind, bamboo, low cost, and recycled materials. In design, we have the design and fabrication, analysis of drag forces, and the output of the Savonius-type vertical axis wind turbine and the electrical energy stored in battery. Next slide, please. Aerodynamics is an important parameter in designing a wind turbine. The aerodynamic force of the rotor blades converts wind energy into electricity in a wind turbine. In drag force, drag is the force that opposes motion due to an object's shape, material, and speed. In fluid mechanics, drag is defined as the force exerted on a solid object in a direction of the relative flow velocity. This drag force is determined by the turbine's frontal projected area and drag coefficient. Drag force is expressed by the formula seen in the PowerPoint. When air collides with an item, pressure is created. However, applying a lot of pressure to the back of the blade will propel the object ahead, minimizing drag. The more perpendicular a forward-facing turbine is to flow, the more pressure the consequently drag it will cause. For the drag coefficient is proportion of aerodynamic drag to the product of the moving airstream dynamic pressure and projected frontal area. It is expressed by the formula seen in the PowerPoint. The drag coefficient is usually proportional to the surface area. On the other hand, many researchers estimate the predicted frontal area to estimate the air gap. The CD of the more streamlined things will be lower, whereas the CD of less streamlined items will be higher. Next slide, please. As a simplest turbine, Savonius wind turbine works due to the different forces exerted on each blade. The concave part to the wind direction caught the air wind and forces the blade to rotate around its central vertical shaft. Otherwise, the convex part hits the air wind and causes the blade to be deflected sideways around the shaft. The blade's curvature has less drag force when moving against the wind or F convex than the blades moving with the wind or F concave, as seen in the PowerPoint. Hence, concave blades with more drag force than the other half cylinder will force the rotor to rotate. Next slide, please. Bamboo has its good features, but it's also very complex material with factors affecting its mechanical properties. The International Organization for Standardization, known as ISO, drew up its standard for determining the mechanical properties of bamboo in 2004. The ISO 22157 standard describes how bending strength, compression, tension, shear, and durability must be determined. For compressive strength, the compressive strength of bamboo is significantly influenced by the age and moisture content of bamboo samples. The compressive strength of bamboo with low moisture content is greater than the bamboo with high moisture content. For tensile strength, the bamboo's maximum tensile strength is measured by testing the fibers, which is the bamboo strips, rather than full cone samples. For the shear strength, the maximum shear stress for bamboo is significantly consideration when designing suitable joinery systems and connectors. For bending strength, the bending strength has a significant influence on the behavior of a building. Therefore, the deflection of each part of a structure must be predicted before it is created. Next slide, please. The Savonius-type turbine is a vertical axis wind turbine that utilizes drag force to move curved blades vertically mounted on rotating shafts. Aside from its omnidirectional and self-starting capability, a three-bladed design allows for higher efficiency on both low and high wind speeds. The theoretical maximum power of the turbine can be derived from Betz law, where the density of air, wind speed, height, and the diameter of the turbine are factors. Next slide, please. Next slide again. Gears are coupled to the turbine shaft and generator to gain mechanical advantage and improve the efficiency in producing electrical energy. The turbine uses a gear ratio of 3:1 to drive the generator at low wind speeds efficiently. Next slide, please. The kinetic energy generated by moving air generates electricity using wind. Wind turbines, wind energy conversion systems convert into electrical energy. The blades of a turbine are initially hit by the wind, causing them to rotate and turn the turbine, which are connected by turning a shaft attached to a generator. Kinetic energy is converted to rotational energy, and electrical energy is generated via electromagnetism. Next slide, please. In designing wind turbine generators, the tip speed ratio is important. The torque increases when the torque increases. The wind passes through the gap between the rotor blades if the wind turbine's rotor moves too slowly. The tip speed ratio can help wind turbines produce more electricity and be more efficient. The tip speed ratio is calculated by dividing the speed of a turbine blade tips by the wind speed. Power coefficient is one of the main parameters which define the performance of a Savonius wind turbine. The power coefficient measures the efficiency of how well a turbine transforms wind energy into electricity. Next slide, please. Torque is where, when the wind force increases, the torque increases while the rotational speed stays the same. Mechanical power is generated in addition to electrical power. Moreover, this means that the generator can generate more electricity, and the torque is determined by the formula seen in the PowerPoint. In static torque coefficient, when the rotor is not rotating, the static torque is the highest torque it can produce. The static torque coefficient is a ratio of actual static torque to theoretical static torque. The turbine starting capability is defined by its static torque coefficient. The static torque coefficient is determined by the formula as seen in the PowerPoint. Next slide, please.
So this will be the flowchart for the methodology wherein the researchers will first start at the area selection, which will be needed for the next step, which is the wind turbine design. Next is the gathering of materials, fabrication, prototype testing, and lastly, the collection of data analysis and collection. For the area selection, due to the openness and accessibility, this section of Circumferential Road 6 was chosen, which is in the median of the second lay-by station from the lower Bikutan entrance. In this table, the obtained wind speed is presented. The researchers used anemometer to measure the wind speed. The researchers used the obtained highest maximum wind speed for the designing in the wind turbine blades, and also it is used to withstand strong winds. Here is the calculation in order to get the measurement of the wind turbine. So assuming that the turbine efficiency is equal to 25% and the generator efficiency is equal to 85%, the calculated power will be 5.6941 watts. Using the kinetic energy formula, the calculated swept area is 0.071 square meters. Also assume that the aspect ratio is equal to 1. The root of the swept area will be 0.2648 meters, which will be the diameter and the height of the rotor. Assume that the overlap ratio is equal to 15. The diameter of blades is equal to 0.1431. meters, and using the formula of overlap ratio, the calculated gap is equal to 0.0215 meters. And lastly, the end plate is computed to be 0.1574 meters. For the fabrication, the blades of the wind turbine will be made of bamboo and its diameter will be 0.1431 meter. For the rotor is the non-stationary part of the model in which it has a diameter and height of 0.2648 meter. For the end plates will be made of scrap metals, and it has a rotor diameter of 0.1574 meter. And lastly, the base will be made of recycled umbrella stand, which will be filled with cement. For the prototype testing, the researchers will conduct tests. First, the tip speed ratio test. The tip speed ratio will help the researchers maximize the power output and the efficiency of the wind turbine. Second is the power coefficient test. The power coefficient test will help the researchers measure the wind turbine's efficiency. And lastly, the static torque test, which will be used for the self-starting capability of the wind turbine. So these are the references used in this study. In this slide shows the Gantt chart, and shows this slide shows the total expenses. That's all. Thank you.